We are going to begin this semester in Precal with a unit called Linear Equations and Analyzing Graphs. In this section, you review some key concepts, formula, rules, ideas that you have learned during the years you have studied math. First of all, let's take a look at the Cartesian plane. This is known as the rectangular coordinate system or the Cartesian plane. There are 4 quadrants, starting with the upper right and moving counterclockwise. Each quadrant is labeled 1, 2, 3, or 4. The x-axis is like a horizontal number line and the y-axis is like a vertical number line. We plot points on this plane in the form of x, y. In higher level math class, we will begin to talk about points as directed distances. The x component is the distance direction from the y-axis, and the y component is the distance direction from the x-axis. Now let's look at the Pythagorean theorem and how we use that to solve word problems. We're going to use the formula a squared plus b squared equals c squared to help us solve 2 examples. In example 1, a baseball diamond is actually a square with sides of 90 feet. Let's look at a picture of this. If a runner tries to steal second base, how far must the catcher at home plate throw to get the runner out? In order to solve for C, we have to use the Pythagorean theorem, where A equals 90, B equals 90, and we need to find the value for C. To use the Pythagorean theorem, all we have to do is substitute the values for the side lengths into A and B. Therefore, we have 90 squared plus 90 squared equals C squared. Well, 90 squared plus 90 squared is 16,200, and that equals C squared. So to find C, we have to take the square root of both sides of our equation, and after we do that, we get 127 rounded to the nearest whole number is approximately C. So C is approximately 127 feet. That's the length the pitcher has to throw the baseball from home base to second base. Given this information, explain why runners more often try to steal second base than third. I would like for you to use this part of your notes to give your own explanation of why you think that runners prefer to steal second base rather than third base. I will be checking this tomorrow when you turn in your notebook. The next problem we're going to do is example 2. Your family wants to purchase a new laptop with a 17-inch widescreen. Since the 17 inches represents the diagonal measurement of the screen from the upper corner to the lower corner, you want to find out the actual dimensions of the laptop. When you measured the laptop at the store, the height was 10 inches, but you don't remember the width. Let's take a look at a picture of what this looks like. We're going to use this diagram to help us calculate and describe how we can figure out the width of the laptop to the nearest 1/10 of an inch. Since the diagonal, the measurement of the widescreen, is 17 inches, we're going to use that number as our C. We're going to use the 10-inch height as our B value, and we need to solve for A. So we're going to use the Pythagorean theorem, and we're going to solve for this side. How wide is the widescreen? Using the Pythagorean theorem, we substitute 17 in for C squared. We substitute 10 in for the b, that gives us 10 squared, and we're going to solve for a. So we set it up just like this. We're going to subtract 10 squared from both sides of our equation. That leaves us with a squared equals 17 squared minus 10 squared. The result is a squared equals 189. To find a, we have to square root both sides of our equation, and we get that a is approximately 13.7 inches. In this section, we're going to prove that the distance formula is like the Pythagorean theorem. We're going to use 2 points on a Cartesian plane, and we would like to find out what the length is, or the distance is, between those 2 points. So let's look at a diagram. Here you can see that the red line between the 2 points represents the distance between those 2 points. The blue line represents the difference between the y values, the difference between 2 and -3. The green line represents the difference between the x values, the difference between -2 and 3. We're going to use these points and the distance formula to determine the length or distance between the points. The first step is to label your points. We've labeled the first point x1, y1 for point 1, and we've labeled the second point x2, y2 for point 2. Now we're going to enter these numbers into the formula. These numbers right here, we're going to enter them into our distance formula, and we're going to show how this difference here is basically our a value and our b value in the Pythagorean theorem. It's the same thing. Okay, so we have entered our values for our x2, our x1, and our y2 and our y1 into our distance formula. What you want to watch out for here is when we are entering a value that's negative. You want to make sure that that negative number is in parentheses. Okay, you also want to make sure that you're very careful when you Now that we have our points labeled, we can enter them into our formula and solve for the distance. So I'm going to take this x value right here, this 3, and I'm going to insert it right here. And then I'm going to enter the value of -2. Now remember, this is minus. So we're actually going to have minus a -2. Minus a -2. For the y values, we start with a -3 for y, and we subtract 2. Subtract 2. This is going to give us 5 squared plus a -5 squared. Now be careful with this -5. It needs to be in parentheses. Whenever you square a negative, you need to put the negative number in parentheses. Don't forget. What we end up with is d is equal to the square root of 50. And I'm going to just leave it as a square root of 50. You can simplify that in your calculator if you like to get a decimal, but I'm just going to leave it as the square root of 50. Now I'm going to use the Pythagorean theorem to solve the same problem. Notice that the distance between -2 for the x value and 3 is 5 units. From -2 to 3, we have 5 units. For the y values, from +2 to -3, we also have 5 units. So both of these side lengths are 5 units. So I'm going to use this value as my a value, this value is my b value, and then I'm going to solve for c, which is actually the same thing as d for distance. So here we solved using the Pythagorean theorem, and voila, we ended up with the exact same solution. So just remember, the distance formula is derived from the Pythagorean theorem. That might also help you remember what signs need to go into the formula. This is an area where a lot of students make mistakes. They put plus signs in here instead of minus signs, or they put a minus sign here instead of a plus sign. So just be careful of that and make sure that you know that this value right here is the difference between the x's, and this value right here is the difference between the y's. And that's all there is to it. Next, let's look at the midpoint formula. This formula gives us a point. It's the point in the middle. So your answer should always be in the form of an x, y coordinate, because that represents our point. So I know you have been using this for a long time, but let's review. We'll do a couple problems. So once again, we label our points x1, y1, x2, y2, representing our first point and our second point. And we put those values into the formula for our x's and y's. Since we're adding here, it doesn't matter if we put x2 first and then x1, or if we put x1 first, then x2, because we're adding these together. Just put the x's together with an addition. We're going to add those two numbers together and then divide by 2. That will give you your x value for the point that's in the middle. Do the same thing for y. So in this case, we got -2.15 for our x value and 3.15 for our y value. In this next example, we have the midpoint, and we have one endpoint, and we have one value for the other endpoint, but we need the x value. So what we're going to do here is we're going to use the midpoint formula again, but since we're only looking for an x value, I'm only going to use the x part of the midpoint formula. So here you see we have these points, and I'm using P from the first point, and I'm adding to it the -1 for the value for x from the second point. And I'm dividing by 2. The result that I should get is the x value for the midpoint, which is the -2 here. So what I'm going to do now is I'm going to solve for P. All right, so the way we solve for P is we want to eliminate this 2 in the denominator. And the way to get rid of that is to do the opposite operation. Now this operation right here is a divided by. So if I want to get rid of the 2, if I'm dividing by 2, I need to do the opposite operation, which is multiply by 2. So I'm going to multiply both sides of my equation by 2. The result is I have P minus 1 remaining equals a -4. Well, my next step is to add -1 to both sides, and so I end up with P equals -3. Now this solution makes sense because -2, as you know, is in between the numbers -3 and -1 on the number line. So we know that our answer is correct. In this next example, we're going to use a circle, its radius, and its tangent line to find the equations of the circle and the equation of its tangent. Now, this is something that you should have studied during geometry, so you should be fairly familiar with this type of problem. So here we have a rough sketch of a circle on a Cartesian plane with a center at -1, 2, and the point 3, 4 is on the circle. We already have part of what we need to write our equation for the circle. We have the center, which is also the same as HK. So we take the center point and we plug that in for HK. So here we have x minus a -1 squared plus y minus 2 squared equals r squared. This, of course, simplifies down to x plus 1, so we have x plus 1 squared plus y minus 2 squared equals r squared. The problem is we don't know what the radius is, so we have to figure that out. Well, we're going to use the Pythagorean theorem or the distance formula to do that. R is this distance between the center point and the point on the circle. So this is the same thing as the hypotenuse of this triangle that's formed by the radius. So we can use the Pythagorean theorem to help us find this length, the length for the radius. So let's go ahead and do that. So using the Pythagorean theorem or the distance formula, we find that the radius is the square root of 20. Now we're ready to write the entire equation of our circle. So the last part we needed for our circle equation was the radius. So the radius is the square root of 20, and so in the circle equation we would write that as the square root of 20 squared. Well, the square root of 20 squared simplifies down to just 20. So our final equation for our circle is x plus 1 squared plus y minus 2 squared equals 20. In the next example, we have to find the equation of the line that is tangent to the circle found in the above example at the point 3, 4. So we have a diagram of the same circle, except this time we have a tangent line drawn, which is a line that is perpendicular to the radius. So in order to find the equation for the line tangent, we're going to have to use some information about our radius. We know that these perpendicular lines have opposite reciprocal slopes. So if we can find the slope of the radius, we can also find the slope of the tangent line. We're going to use the slope formula to determine what the slope of the radius is, and we're going to use our two endpoints, -1, 2, and 3, 4, in the formula to find the slope. And here you see we found the slope to be 1/2. So if the slope of the radius is 1/2, then the slope of the tangent line must be -2. Now we can use the point slope formula to find the equation of the line for the tangent. We're going to substitute in one of our endpoints, and I used point 3, 4, into the point slope formula and then simplify. So y minus 4 equals -2, which is our slope, times x minus 3. After we simplify this, we get the equation y equals negative 2x plus 10. Don't forget the other common formulas that you may need to use, such as area, perimeter, and volume. Now let's take a look at some graphs of equations. When we graph an equation in two variables, we are making a graphical representation of the equation. The solutions to the equations are the values for which the input, usually the x value or the independent variable, results in an output, usually y, or the dependent variable. We call these points solutions or solution points. In example 1, we're going to determine if the given point is a solution for the given equation. In example A, we merely plug in the y value in for y and the x value in for x, and determine if those two sides of the equation are equal to each other. And as you can see, as you simplify this equation, we get a 13 equals 13. So yes, this point is a solution. In example B, we do the same thing. We plug a negative 3 in for y, a negative 1 in for x, and as you can see, when we square the negative 1, we get a positive 1, and a positive 1 minus 1 is 0. So negative 3 does not equal 0, so no, this is not a solution. In the next example, we're going to sketch a graph of y equals x squared minus 2 by creating a table. Okay, so I created a table, and in my table I used the values negative 2, negative 1, 0, 1, and 2 for my x values. I plugged those x values into my equation for x squared and solved for y. And the results were 2, negative 1, negative 2, negative 1, 2. I then plotted these points on the graph, negative 2, 2, negative 1, negative 1, 0, negative 2, 1, negative 1, and 2, 2. And this graph forms a parabola. So, if you have only 4 points, is that enough points to tell what the shape of this graph is? What I want you to do is tell me, are these enough points? Why or why not? We're going to use this question for class discussion. To find the x and y intercepts for the graph of y equals x to the third minus 4x, we first have to make y 0 to solve for x, or make x 0 to solve for y. So let's look at the x-intercepts first. We're going to make y equals 0, and we're going to solve for x. So I put 0 in for y, and then I have 0 equals x to the third minus 4x. Well, we have to factor out one of the x's first. That gives us 0 equals x times, parentheses, x squared minus 4, close parentheses. At this point, we have to factor again because we end up with a difference of squares. When you have a difference of squares, that factors again. So we have 0 equals x times, parentheses, x minus 2, close parentheses, parentheses, x plus 2, close parentheses. That gives us 3 zeros for our x value. We have an x equals 0 as one of our zeros. We have an x equals 2. When we solve for x here, we get 2 because 2 minus 2 is 0. And for this one, we get negative 2. So our points are 0, 0, 2, 0, and negative 2, 0. Now to find the y-intercept, we make x equals 0 and solve for y. This one's a lot simpler because when we make x 0, we simply end up with 0. So our y-intercept is 0, 0. Notice that 0, 0 is not only the y-intercept, but it's also the x-intercept. This is the only point on the graph where the x and the y-intercept are the same. This point is called the origin. Now let's take a look at graph symmetries. Some graphs have symmetry about the origin or about one of the axes, and some graphs don't have any symmetry at all. So we're going to look at some graphs and analyze whether or not they have symmetry and about which axis they have symmetry. We are going to be taking a look at 3 different kinds of symmetry. The first kind is symmetry with respect to the x-axis. The second kind is symmetry with respect to the y-axis. And the third kind is symmetry with respect to the origin. First, let's take a look at symmetry with respect to the x-axis. If the point xy is on the graph, the point x negative y is also on the graph. So we can determine this algebraically by replacing y with negative y into the equation and see if you have the same result. So let's try that. In this example, we use the point 5, 2. If we put 2 in for y and 5 in for x, we get 5 minus 2 squared equals 1, which is a true statement. If we substitute a negative 2 in for y, we still get 5 minus, even though this is a negative 2, when we square a negative 2, we still get positive 4. So 5 minus 4 equals 1. So yes, this particular graph has points that are symmetrical with respect to the x-axis. Next, we are looking at symmetry with respect to the y-axis. If the point xy is on the graph, the point negative xy is also on the graph. This would give us symmetry with respect to the y-axis. So entering these numbers algebraically, we're going to use 7 for y and 2 for x. So 7 equals 2 squared plus 3. This is true. If we substitute the x value with a negative 2, we still get 7 equals 4 plus 3. So yes, these particular points are symmetrical with respect to the y-axis. In our last example, we're looking at symmetry with respect to the origin. If xy is on the graph, the point negative x, negative y is also on the graph. In this case, we would have to replace y with negative y and replace x with negative x to see if we have the same result. Let's use y equals x to the third as our equation. Okay, here you can see that we used a 2 for x, and 2 to the third power equals 8. So if we enter a negative 2 for x, we actually get a negative 8. So by replacing the 2 with negative 2 and replacing the 8 with the negative 8, we get true statements each time. This means we know that our graph is symmetrical with respect to the origin. In the next example, we're going to determine what, if any, types of symmetry this given equation has. Y equals x to the fourth minus x squared plus 3. In this example, I used 2 for the x value and 15 for the y value. And when I replaced my y with the negative y, the resulting statement was not true. So no, this particular graph is not symmetric with respect to the x-axis. With respect to the y-axis, it was symmetric because when I replaced the x value with negative x, I get a true statement. That means that this graph is symmetrical with respect to the y-axis. When I checked for symmetry about the origin, of course the answer was going to be no, since this particular graph is already symmetric about the y-axis. So it can only be symmetric about one of the axes at a time. So if it's already symmetric about the y-axis, it can't be also symmetric about the origin. Using the same information, knowledge, and mathematics step as the previous problem, we can categorize functions and their graphs even further. A function can be called even if it is symmetrical with respect to the y-axis. A function is said to be odd if its graph is symmetrical with respect to the origin. If a function is neither even nor odd, then it is said to be neither. So we have tests for even and odd functions. A function y equals f of x is even for each x in the domain of f where f of negative x equals f of x. And a function y equals f of x is odd if for each x in the domain of f of negative x equals negative f of x. Okay, well, one of the ways we can do this is to go ahead and use a simple number like the number 2, plug it in for x and see what we get for y, and then check it. Looking at this first example, we plugged a 2 in for x in the equation g of x equals x to the third minus x. Okay, so we've substituted a 2 in for x, and we got the number 6. Is it even? Well, if we replace 2 with a negative 2, we don't get the number 6. We get the number negative 10. So therefore, this function is not even. Is it odd? Well, if we replace the 6 with a negative 6, and we replace the 2 with a negative 2, lo and behold, we get that negative 6 equals negative 6, and this is true. So yes, this is an odd function. Now you try the next two problems, problem 2 and problem 3. We'll check them in class to see if you got it correct. This concludes our lesson. We win at the ranch. Go Longhorns!